So let's resume our school. So now it's my pleasure to introduce Dr. Andrew Szentgyorgyi. Is that right? Pronunciation? So he's from Department of Astronomy in Harvard, or SIO. Smithsonian, isn't it? But in the Harvard University webpage, so sorry about that. So the Smithsonian. He has worked in several areas of astrophysics, but lately on the measurement, high-resolution spectroscopy of stars for measuring radio velocities and stellar structures. And in particular, he is the PI of the XVIII instrument, which we are going to hear about. Thank you.
Now people can probably. So, we just go like this. That's great. Super. Okay, well, it's a pleasure to be back in São Paulo after, I think, 8-10 months. See some old friends in the audience. Looking forward to meeting some new people. What I wanted to talk today about is modern exoplanet science in a solar system context. Because in some way, what's interesting about exoplanets is how it compares to our solar system. We are sort of egocentric. So first, what I'd like to do is give you a historical context, and then talk about a brief introduction to exoplanet science today. Then provide the solar system's context, and then go back in a little more detail about exoplanet science today. Talk a little bit about orbital resonances, and I will not talk about planet formation. Sorry about that. So the first thing, it's sort of obvious, but let me just say that, maybe hold this thing up a little easier. The first thing to say is that an exoplanet is obviously a planet orbiting a star other than the sun. But then, people say, well, people have a lot of questions about what distinguishes an exoplanet. And so the first thing is that a planet is less massive than a star, and is more massive than a planetesimal, a thing like Pluto. Has no internal burning ever, okay? Because many things that are stars aren't burning anymore, but burned in the past, internally. Finally, they're shaped by gravity. They're spherical. Although there are, in fact, planetesimals, they're also spherical. And it's formed in a protoplanetary disk as opposed to a star, which forms a disk. So, next. Is this on, too? Did I do that? I'm speechless. Nope. Yeah, is it advancing then? Right. I actually own it, but it's not. Oh, there. Okay. So, first a little paleo history. You sort of start, there were Greek philosophers who thought about exoplanets. Of course, you have to have a heliocentric theory to really think about exoplanets. Giordano Bruno speculates about the inevitability of Earth-like planets around other stars. It gets burned at the stake for that and other things in the early 16th century. Newton says that exosolar systems will not only harbor exo-Earths, but they will be identical to the solar system. Finally, Struve argues that there's no reason exoplanets should not be much closer than a hot star than Mercury is to the sun. And finally says that super Jupiters in close orbit should be detectable by Doppler spectroscopy. He was a smart guy. That all in sort of the 50s. But we have this long desert. So in the late 19th century, Jacobs discovers a planet astrometrically discovers a planet orbiting 70 Oph, which is rejected. Struve thinks he's found a planet around 61 Peg, but of course it turns out to be fake too. In the 50s and 60s, Peter Van de Kamp kept making claims that Barnard's star was hosting a Jupiter mass planet, about a Jupiter mass planet, which is subsequently disproved. And then finally, this is probably the saddest story in exoplanets. Campbell and Latham, Campbell studying Gamma Ceph, and Latham observing HD 114762, which turns out actually to have an exoplanet, thinks they might have found exoplanets, but they're sort of afraid to actually make the claim. So actually the first exoplanet, we always forget about this, was not found orbiting a normal a dwarf star. It was found orbiting a pulsar by Frail and Wolfson. But the watershed comes in 1995 when Caloz and Mayor discovered a planet orbiting 51 Peg, which I'll get back to in a second. But much to his surprise, they bears out Struve's conjecture, and it turns out that this is a planet with a very few-day orbit, the size of Jupiter orbiting a star like the Sun, which is kind of a surprise. So then in 1999, we find multiple star systems. Finally, in 1999, we measured the radius of an exoplanet. These previous measurements measured the mass of an exoplanet. I'll get into that in more detail. But this is now we're measuring the radius of exoplanets. We finally have imaging of exoplanets. They're discovered by microlensing in the early aughts, I guess is how we refer to it. And then finally, the Kepler deluge, which I'll have a lot to say about, happens in 2009. Kepler is a satellite. Up to the time of Kepler, they discovered a couple of exoplanets a year. It's very arduous. All of a sudden, Kepler dumps 4,000 exoplanet candidates on us. And in 2014, fulfills the goal of discovering a Earth-sized, Earth radius, but not necessarily Earth mass planet, or in the habitable zone of a FKT star. And then most recently, TRAPPIST-1 system is found, which has 3 habitable zone planets. Remarkable result. So exoplanet science today, as I said, now the catalog of exoplanets is really large and spans a lot of dynamical range. This is the relative size. Now, this is the radius, not the mass. Jupiter, Neptune, Earth, these are all Kepler stars and a wide range of orbital periods. This number, 4,032, probably is different today. It seems to change on a daily basis. And we find, and I'll talk more about what these things all mean in a little bit. These little dots are color-coded by how the stars of the exoplanets were discovered. But we find hot Jupiters very close in short orbital periods. We've also found normal Jupiters with long orbital periods like our Jupiter, ocean worlds and ice giants with a range of periods. Closer to the star they are, they're more likely they are to be liquid. Rocky planets and potentially lava worlds. And the interesting thing is Kepler found, again, remember radii, Kepler finds very small exoplanets. Kepler 37b is almost moon-sized, which does hold out the hope that someday we'll fulfill the dream of discovering exomoons, something that David Kipping has been working on very hard. But the bottom line, the important thing and the important message for all of us that are interested in GMT is while we've got these radii, their masses cannot be measured with currently available telescopes. That's why I think we're building the GMT. And then the other issues of habitability, which is because, from personal perspective, I see we find exoplanets, we measure their mass, we measure their radius, we find them in habitable zones, we see whether they have biomarkers as evidence of biotic activity, and then we see if there's intelligent life there. Not always sure there's intelligent life here on Earth, but, and right now, the number, there was a long desert where we didn't find any habitable zone planets. Now they just seem to drop out of the sky. There are lots of them. And the one thing, I'll repeat this again and again and again, although Kepler and the soon-to-fly TESS mission, the European Cheops mission, and Plato, all exoplanet measuring, discovery, and characterization satellites, you don't have to be in outer space to find truly fascinating things. As I said, this TRAPPIST-1 system, which is a system around a M dwarf, it's actually an M8, here's our solar system. This is the whole size of the TRAPPIST system, but has in fact 7 terrestrial, probably terrestrial planets, 3 in the habitable zone. And that was done, it's done with a very modest observatory in Morocco. This is, I think, a 1.2 meter telescope. So, planets versus stars. Stars don't burn nuclear. Stars don't burn nuclear. Shouldn't write slides too early in the morning. Planets don't burn nuclear fuel. And, the thing is that, well, people say, well, what's the difference? There's Y, L, and T stars. What's the difference between, Y is 1828, which is, it's kind of the temperature of the Earth, and Jupiter, and they're about the same size, and it's, the truth of the matter is Y's 1828 may in fact be a free-floating exoplanet. But all of these things either are burning deuterium, or in many cases, these really, really cold objects aren't really burning anymore, but they have burned deuterium in the past. Jupiter, to the best of our knowledge, has never burned anything in its interior. Now, some of these large planets, as we'll see later on, are in fact self-luminous, but that's due to heat from gravitational attraction, which is a different thing. Oh. Now, the other thing is that stars have disks and planets form in them. So this is a beautiful picture of the HL Tau system taken with ALMA, and here you can see the protostar in the middle, and then you see the debris disk surrounding it, and you see these little like grooves in a record, for those of us that remember what records look like. And these are, it's highly likely, I'm almost certain, that these are furrows cut out by planets as they're drawing material out of the protoplanetary disk and turning themselves into planets. And finally, the question of, what's a planetesimal and what's a planet? Planets their morphology is determined by gravity, so they're spherical. Most planetesimals are in fact not. Pluto, which I'm going to go into in gory detail, is in fact spherical, but really is a planetesimal for other reasons. So let me talk about the solar system context, and here's a first clue that I'll beat on a little more. This is our old solar system when it had 9 planets. We see that all the planets are pretty much in coplanar orbits, with the exception of Pluto, which is slightly inclined, but you could argue things one way or another. People worried about this for a long time, and for years, all we knew about what constituted our solar system was Bode's law, and this is sort of numerology. You can look at this arithmetic here, but Bode's law said that there was a regular sequence of numbers that governed the spacing and periods of the exoplanets. And you have to realize that when he asserted this law, we were we knew Saturn, and I think we knew about Uranus at his time, but we didn't know about Neptune and Pluto, which are clearly fairly divergent. So this law looked like more than magic, and so people thought this, some kind of voodoo in this numerology, like Stonehenge or something. It all lines up, harmonic convergence. But with Neptune and then finally with Pluto, we find a significant divergence from Bode's law. Now, of course, a simple solution would be to say Neptune is okay and kick Pluto out of the club, which is what we effectively did. But there's nothing to Bode's law. Stan Dermott has this huge calculation of what the likelihood that Bode's law means anything in his book on stellar dynamics. So here's this, my engineers always refer to it an eye chart, which is basically that very, very young people can read the numbers, and most of us can't, so let me blow it up a little bit. And so look at the major constituents of the solar system, Mercury, out to, and we'll include Pluto for the time being. They have a whole sort of range of, there's no real sense to any of these numbers, although, bigger planets seem to be farther out except when they're little. Scaling to an Earth mass, Mercury's a 20th of Earth mass, Jupiter is 300 Earth masses. And there's a little bit of a pattern emerges when you start to look at the densities, but Mars is fairly low. I don't know. These planets seem to be lower density, these seem to be higher density. So you actually can start to sort things a bit, because these are rocky planets. And these we have known for quite a while, are gas giants. And then out here you have these things called ice giants. Now the next thing is that you look at how many satellites the different planets have. This chart, when I copied it from somewhere else, obviously, did not have the correct number of moons of Pluto. Has 5 moons. If you, the thing that, this chart, many of these charts leave out Styx, Kerberos, Pix, and Hydra. Even very tiny things. Ida, for instance, has a little tiny captive moon, and it's not particularly rare for very small planetesimals and Plutinos to actually have moons. But the thing that comes out, the pattern that sort of emerges is big planets have lots of satellites, small planets do not. And then, let me go back to that. And basically when you consider the spin period, and whether they're prograde, retrograde, aligned or perpendicular or aligned to their plane of their orbits, every configuration seems to be present. Now, I think the first real scientific fact that comes out of all of this, and it turns out to be a lucky accident because, get to in a minute, the rocky planets are all inside 1.5 astronomical units. The gas giants all are out, 5 AU or greater. And so I think it's still a fact that despite the existence of hot shooters, I don't think, it's fact that despite the existence of hot Jupiters, which are a puzzle, that rocky planets, refractory material planets, form closer to the sun, and there's an ice line somewhere, and outside the ice line, methane, carbon dioxide, ammonia, water all freeze out, and so you end up with these either gas giants or what we'll come to call water worlds. Let me skip that. Now when we go and look at the, I'm sorry, went a little too fast. When we look at the eccentricity, Mercury is fairly eccentric, but nonetheless, most of the constituents of the solar system have very low eccentricity. Pluto certainly stands out. When you look at the inclination of the orbit, again, Mercury has a larger inclination than most of the other planets, but again, Pluto sticks out like a sore thumb. So the bottom line is that Pluto is different. And so the IAU in 2006 kicked Pluto out of the club, mostly motivated by the discovery of Eris, which is 27 times more massive than Pluto, but obviously not a planet. Even though the New Horizons probe that flew past Pluto shows this really sort of amazing cold but Earth-like topography. Pluto also actually has an atmosphere, sort of an amazing thing given how small it is. Now, we've come to recognize that there are a lot of trans-Neptunian objects, planetesimals, Plutinos. People use different terms to describe them. This is not a complete catalog by any stretch, but many of these things, some of them really quite small, have moons. So the thing that really distinguishes these things, to my way of thinking, is the dynamics of their orbit. When you look at, for instance, Eris, the example that killed Pluto's membership in the Planet Club, you see that it's huge, it's orbiting way outside Pluto, but it's got this orbit that's highly inclined, highly eccentric. And as the evidence started to mount up, versus with the discovery of Sedna, there's Eris, this little teeny orbit, these huge orbits way outside, highly inclined and way outside our solar system. So Pluto more and more starts to look like a planetesimal, not a planet. And this is unfortunately not the most readable thing in the world on the screen, but if you look at the semi-major axes and the inclination of the trans-Neptunia objects, you see that it's almost a scatter plot. So it's important to remember it's not particularly germane to exoplanet science today, but there's recently been a paper, for instance, that there's people believe that they've actually seen exocomets. So seeing exoasteroids or zodiacal disks in the future, not out of the question at all. And the asteroids really tell us a whole lot about the formation history of our solar system. They have these sort of goofy names. They're the Trojans that are almost essentially in the same orbit as Jupiter. The Hildas, they're in this kind of tricorn arrangement. I hope the movie will play. And then the main belt asteroids. These little green guys on the inside are the Hungarians. My father was a Hungarian. So there's this really, really nice taxonomy. People are actually starting to understand how asteroid. There's been an explosion in the discovery of asteroids, mostly motivated by the United States Congress. Once in a while, they do good things for science, and they're worried about humanity being obliterated by a killer asteroid. I don't know what we do when we find one, but at least we'll know we have 24 hours. But anyway, so there's a lot of, and so you really start to see this beautiful sort of taxonomy where you begin to start to. These are the fossils of the dynamics of our the evolution and formation of our solar system. And so the current thinking is partly motivated by the discovery of hot Jupiters, but not entirely. Was that that the solar system has some kind of history where Jupiter gets formed out past the ice line, dives in almost to 1 AU. This is called the Grand Tack. For mysterious reasons, turns around, stirs the asteroids up to the sort of boulder-sized debris of the formation of our solar system, then migrates back out again, but doesn't actually turn into a hot Jupiter. Let me skip that for we're interested in comets for an egotistic reason, because one of the predictions or postdictions, because we're talking about history here, is that when Jupiter and Saturn mostly do this grand tack, they draw comets in and actually hydrate the Earth. Maybe not. There's some of my colleagues say that the grand tack is pure. Well, not well supported. So if we look at the whole space between the stars out to Alpha Centauri, we see our planets. We see a bow shock, the heliopause, which we now have satellites that have left. We do live in a sort of a local cloud, and then finally we get out to the next star. Let me skip that for a second. So, having marched through that, as I said, 2006, they kicked Pluto out, being made to sit at the little planets table. But one really fascinating question is there a Planet 9? Now, is this movie going to play? Can we play the movie? Planet 9 movie. Unfortunately, none of my movies play. So, there's a cursor. There's hope. Well, lights, camera, action. Anyway, well, let me just, oh, okay, here we go. So one of the things that's emerged is we got rid of Pluto, so we went down to 8 planets. How unhappy. But, you know, the minute you get rid of a planet, people start saying, well, you know, there are more planets out there. And so there's Mike Brown, mostly Mike Brown has been the provocateur of the idea that there's evidence in, particularly in the trans-Neptunian objects, that there is a ninth planet, which is illustrated so beautifully in the movie we're not seeing, but we will see. Oh, okay. So beautifully in this movie. Okay, next slide. Anyway, there's a really nice movie after the talk. If you want to come over, I'll show it to you. But the bottom line is that in this this movie, it zooms out a little bit, and it shows that in fact all the trans-Neptunian objects, they're sort of all in elliptical orbits, so they're like lobes, like petals of a flower, but they all have they're all kind of point in the same direction, away from something, and so. Mike Brown and his colleagues at Caltech, you know, say that the dynamical possibility of all those lobes being as co-aligned as they are within sort of maybe a solid angle of some significant fraction of pi, but still all in a solid cone, is about 7 times 10 to the minus third. I don't know, you know, sort of 2.7 sigma or something. You know, I wouldn't sell my house and move based on those statistics, but it's a very interesting idea. So a lot of the dynamicists at CFA have been worrying about that. And now, you know, the really exciting thing, there's at least one, we've discovered at least one visitor from outside the solar system. I mean, for a long time, in really recent memory, people weren't sure whether comets were solar system's constituents or not. You know, they thought they might be visitors from somewhere else. And the fact that we haven't found the discovery of actual observation of the Oort belt is a huge issue because, you know, we conjecture an Oort belt, we say it's out there, but is it there? I don't know. But we're pretty good. What's, yeah, right, super. But, you know, we're convinced that comets, well, they come back and they're on elliptical orbits, but Oumuamua, I guess, it's a Hawaiian, carefully selected Hawaiian name that I knew what it meant a while ago, is actually definitely on a hyperbolic orbit. It has no cometary tail, so it's not a comet. It's very low albedo. It has this very funny, if you look at the light curve, where this is, you know, a couple of hours, it varies in both amplitude and period. So they're pretty sure that this is a highly, you know, it's multi-periodic and it has varying amplitude. So it's not rotating about a principal axis, you know. So it's not spin, you know. Even a potato will usually spin, you know, around one of its principal axes. So it probably has an aspect ratio of 10 to 1, and it's so, you know, a couple of football pitches long, but very narrow. And so now this is pure science fiction, but that's what it might look like. There's no way to image this thing. So anyway, so the watershed for, as I say, really the watershed for exoplanet science was Kepler. It stared at this 100-degree field of view, sort of between Lyra, mostly in Cygnus, but Lyra is up there, I think. Chosen to be not in the plane, but close to the plane. In the plane was too dense. Would have been confusion problems, but just off the galactic plane. And they stared for 3 years, just stared, you know, pointed at this one field. They lost a gyro, I'm going to say 3 years ago. They couldn't point this way anymore, so now they don't call it Kepler anymore, they call it K2, and they point at different fields. And, but it was a remarkable mission. They were sort of steering, as I say, they were sort of in the plane, steering in this direction. They looked at there were 1.2 million discernible stars with the about 1 meter aperture of Kepler, and they were only able to monitor 120,000 of them. That's unfortunate. And so this is sort of the map of exoplanet discovery space before Kepler, and then the yellow dots are Kepler. You can see that this all of a sudden there was, I guess, I forget which one this is, but there really were almost no Earth mass planets. Kepler just dominates now. This is seen here in this plot where you look at the differential growth of exoplanet discoveries, and then this yellow bar is the first year of Kepler. Now, there we go. So Kepler uses a technique called the transit technique, which I will beat to death tomorrow. And what it does is all you're looking for is the transit of a planet in front of a star, an occulting disk that reduces the luminosity of the star. And this is sort of a proxy drawing of what the transit of, for instance, Venus would look like. But of course, we don't get to, oh, no, that's the next movie, but not quite yet. Of course, we don't resolve exoplanets except in some very exceptional cases with adaptive optics. So all we get to do is see that plot that we're not seeing right now, but this is a good movie too. This is a movie showing planetary migration. It's a model of a protoplanetary disk, and as the okay. But so Kepler it has this deluge of planets, but again, we only know the radius. Oh, there we go. Okay, let me skip that. The thing is that, you know, the tricky thing is that exoplanet detection is so selection biased. Some fairly heroic work about 5 years ago by Andrew Howard, John Johnson, but in particularly Courtney Dressing with Dave Charbonneau, when it's, you know, given what we know, given what we understand about our selection biases, how many planets are there out there and how big are they? And the conclusion really is, this is a plot of, it's a histogram of planets by planet radius, plotted in different, color-coded into different expected periods. And the conclusion is that most exoplanets are Earth-size, and a lot of them are in the habitable zone, which, given, you know, in the early days, the selection bias was that we were only discovering hot Jupiters, really massive things in really short orbits because they were really easy. But the prospects for finding Earth 2.0 is now look very rosy. So most planets are, in fact, Earth-size. There are some, you know, bizarre exoplanets. Kepler 64b, circumbinary Earth 4-star system. There is a planet orbiting a binary B-dwarf system. We have detected planets orbiting red giants, and GJ1214b is almost certainly a water world. Now, oh no, I don't have, that slide's later on. Now, the really fascinating thing is that if you know the radius and you know the mass, then you obviously know the density. But some work that was pioneered by Dimitar Sasolov to examine what you could do with that information. He was working with a geologist. Geologists love these things called ternary diagrams, where you, for instance, you imagine that worlds are made out of water, some core stuff like iron, and some mantle stuff like perovskite or sand. And you say that these are the only three constituents you can make planets out of, which isn't a completely ridiculous assertion. It's kind of borne out by what we think we understand about the solar system. You can then, you make these ternary diagrams where it's all water, all core, all mantle. Water mantle stars are all along this line. Core water stars are all on this line. And obviously, you can have intermediate mixtures of all three of these things. And depending on the temperature of the star, you find out that that you're actually fairly, if you measure the mass and radius of the star, you're actually fairly constrained as to where you can live in these different ternary diagrams. And so if you know the mass and the radius, you actually know a lot about what the planet is made out of. So the Earth, for instance, is a rocky exoplanet. It's got a hot inner iron core. It has a mantle that is made out of different. Dimitaro says it's all perovskite, which is some funny stuff, but it's made out of dirt and rock, I think. And Mars, on the other hand, is another rocky planet. Might have a core, but certainly also has a crust. The one thing to remember is when we talk about water worlds, that Earth is not a water world. Although we're covered in water, it's not very much, and so the ocean is a fairly thin layer on top of the Earth. When we talk about water worlds, we're talking about things that are mostly made out of water. And for instance, Titan, they don't have, and Enceladus is, I thought it was more water. Anyway, we're not particularly, and Mars was reasonably wet in its past, was like us in the past. So the truth of the matter is when we search for analogs for Earth 2.0, we haven't found any yet. This is partly incompleteness. For instance, you will find a one Earth mass star, Alpha Centauri b, which turns out not to exist, but at that time we didn't know its radius. We tend to characterize these things as ESI, Earth Similarity Index. And that's a little bit like who's the best goalie in Brazilian soccer, the best goalie index, BGI. Well, this is ESI. So it depends upon, what you put in the recipe to make an ESI. But the Wikipedia authoritatively assigns a 1.0 to Earth. And then these other guys that are pretty close, but none of them don't actually really score very high. Gliese 581G unfortunately turned out not to exist. So the gas bag planets and the water worlds, sort of the other paradigms for exoplanets characterized by Jupiter and Saturn and Uranus and Neptune. They're mostly these guys are mostly, gas bags are mostly metallic hydrogen, molecular hydrogen, and probably a little metallic core in the middle. Uranus is an awful lot of ice, but methane and ammonia, and they all probably have cores. This is just repeating what I said before, but these are frozen water. Here we go. Yes, this is. Now, when you say water world, if you know what this picture is of, then we know how old you are. But Kevin Costner starred in a movie called Waterworld, where mysteriously the Earth had become entirely covered with water. He's having a bad hair moment here, but in fact, it's really much more. These water worlds, in at least our solar system, is much more like shackles, right? Stuck in the ice. But we know, we've identified actual real water worlds. Gliese 436b. I will talk about that again in a little bit. Orbiting an M dwarf, small orbital period, temperature about 712 Kelvin, and we have a fairly good feeling that there's this hydrogen envelope that shields the shields the planet a little bit, but it's mostly water with a rocky or iron core somewhere in the middle. Skip that for a second. So the thing is, I sort of alluded to this before, 51 Peg, the very first exoplanet we discovered was, in fact, an analog, Jupiter analog. A little bit bigger than Jupiter, a little less massive, but and the stars are fairly similar to solar type stars, but the orbital period is 5 days, and the surface temperature is probably about 1,000 degrees centigrade, pretty hot. And so the first, one of the big debates in the early days was, how can you have a planet like it just can't exist? There must be a mistake. It must, on and on and on and on. It is an exoplanet. It certainly poses a lot of challenges. I think we understand very well how this planet can survive. You sort of, wonder how you can put something like this in the microwave that long and have it not just evaporate, but it in fact doesn't. But aside from its pure survival, the challenges of how migration happens is one of the real outstanding questions in basically planetary dynamics itself. Let's see. Anyway, so let me skip that. Now, the question is what's the difference between hot Jupiters and cold Jupiters? Well, Jupiter is in a 1,500-day orbit. This is one of our favorite examples of a hot Jupiter. It's very bright, very close, very well studied. It has a 2-day period. WASP-12D has a 1-day period. Mercury does not have a 2-day period. That's a typo. But these things are incredibly close to their host planet. They all, the temperature of Jupiter is actually poorly understood, but since we know less about these planets, Mercury is easy. We understand less about these planets, so we're more certain of their temperatures. They're really, really, really quite hot. And so WASP-12B, there's observational evidence that in fact is evaporating. But it certainly also brings up the issue of the existence of this thing called the ice line, which is, we think it exists, that there's warm dust in here, there's ice and snow out here. You make Earths, Venuses, Marses in here. You make Jupiters, Neptunes, Uranuses, water worlds, and gas bags out here. That was an artist's impression. And so the real mystery is, just to sort of underscore this, Jupiter had to be made out here. Jupiter ended up pretty much in the same place, we think. But there's, strong evidence at one point Jupiter was at least that close to the sun. But then hot Jupiters, they don't turn around and go back out again. They just keep on going in. And so this is, Jupiter has to be born out. I mean, our current thinking is has to be born outside the ice line. So the process of planetary migration is truly one of the interesting scientific questions for planet formation in the coming decade. Anyway, you saw that movie already, so we'll skip it. Anyway, this is kind of this cartoon about planetary migration for dummies, and if planets do migrate, whether they grand tack the way we hypothesize, not so sure. But these things are starting to be unraveled in studies of all of the constituents of the solar system. One thing is that I was going to show this. I thought I'd have control of my keyboard. There's this really great. This is a warning. This is a time sink. I was reading a proposal for the NSF, and this was in the proposal, and I said, "Well, let's have a look at that." And then it was noon when I started, and it was dark. When hey, wait a second. The planes came for a long time. This actually allows you to simulate planetary dynamics, and you can take different. The idea of the game is put as many planets as you can in this imaginary solar system, and not have them go outside 2AU. Keep them in the habitable zone. So let me just move on a little bit. I talked a little bit about TRAPPIST-1. TRAPPIST-1 is very challenging. It is in fact way down at the bottom of the main sequence, orbiting M8 star. As I said, looks something like that. Let's see. Now, the really fascinating thing about TRAPPIST-1, though, is another dynamical question: is that how do you get all of these planets to park themselves? If you go back and let me stop for a second and go back for a second. If you play this game, you realize how hard it is to take a whole bunch of planets and put them all together and not have them interact dynamically and kick themselves out. And so the thing about TRAPPIST-1 is that these things are all close together. They're all talking to each other, and the only way you can get them to get stabilized is if they have some very subtle mean motion resonances. And what I wanted to do was, unfortunately, I'm just not going to play either. I'm sort of movie poor here. So this is a really nice movie that shows the main belt, the Hildas, and how Jupiter actually shepherds all of these things, and the fact that these are in 3-to-1 mean motion resonance. These are in 2-to-1, and then there are these guys called the Trojans out here that are in 1-to-1. But let me talk just a little. Oh yeah! Wow, it worked great. So here, this is a really great movie, and this is Jupiter orbiting the Sun. And then there's this kind of curious thing that, as you watch this movie, you'll ask yourself, well, Jupiter's not orbiting; it's going back and forth. That's because this whole movie is in the frame of the co-rotating frame of Jupiter. It's mean anomaly, which is the frame where Jupiter is orbiting in a circular orbit, but in fact here Jupiter in fact is not quite circular, so it's moving back and forth with respect to its mean anomaly, I believe. Then you can see what all these other constituents are doing. So here are the Trojans, and they're all jostling around in these lobes. Well, now there's the TRAPPIST system, and there's Jupiter again. Okay, well, so the mean motion resonances, I believe, mostly arose from dynamical studies of Jupiter, and of course, Ganymede, Europa, and Io are in very low resonances. And let me see if I can. That's a movie too, but I seem to have lost control of my. It is a movie, but the next slide probably is almost as good as a movie, if I can get to it. Try the movie. Anyway, it's very easy to see. Oh, there we go. So, okay, there it goes. And so you can see that, I don't know why they labeled this 1-to-1, of course. So you can see that every time Io goes around once, Europa goes twice, and Ganymede goes around 4 times. So that when one of them gets in a mean motion resonance, when one gets a little ahead, the resonance condition equilibrates their position, if you will, and when it gets behind, they pull each other back onto stable orbits. So that's kind of a simple thing to understand. It's like harmonic sequences in music, the small ratios of the frequencies of the tonic, the third and the fifth, the fourth and the fifth in a scale. But the trouble is that so this is actually not a movie, a really good picture. So here you start out. Io goes around once. Ganymede goes, this is, oh, I can't remember their names right now, it's halfway around, this is Ganymede, I'm pretty sure it's a quarter way around, then they sync up again, and Ganymede is pi out of phase, and then finally 4 orbits, they sync up again. So if there's any, it's sort of a self-tuning system. Anytime they get a little bit out, they tune themselves back up again. And so you saw, well, the thing that's sort of amazing is about the TRAPPIST resonances are very complex, because when you think about it, all these things are dynamic. Of course, they're talking to their nearest neighbors most closely, but they're all talking to each other. And so you have to invent a sequence of integers that somehow is sort of a relatively, the minute a 131, 437 resonance doesn't make much sense, because you don't regulate your dynamics often enough. So it appears that the relative orbits have this sort of funny sequence base 24, and the nearest neighbors have these relationships, and these are decimal equivalents. It seems time for another movie. Yeah, so you can, if you watch it really carefully, you'll see the nearest neighbors. They do sort of have harmonic convergences. Okay, here we go. But it's complicated, and the only thing I can say is it works. I mean, this is a very old star, a very stable system. So it's absolutely incredible that you can have this complicated a set of mean motion resonances. Oh, we didn't need that movie, but this is HD 18328, I think, also exhibiting mean motion resonance. Let's good. Sort of. Let's see. I think where am I here? What's that? I'm done a little faster than I planned to be, because the movies didn't play the way I planned on playing. So the other sort of exciting thing, I'll talk really slowly now to take up the time. Just kidding. Is that the nearest stars seem to host exoplanets, and well, and that's this result on Proxima Centauri that Rebecca was talking about a bit before. So the Alpha Centauri system is 3 stars. They're the 3 closest stars, and Xavier de Mizc had this really bleeding edge result about 6 years. It seems like yesterday, 6 years ago. And worked really, really hard to back out the noise, and discover this periodic signal, the hallmark of Alpha Cen B, star B, lowercase b planet. Unfortunately, it's probably spurious, but more recently, Guillaume Anglada-Escuda has discovered an exoplanet that has held up quite well. These are hard measurements to make. In what is truly the closest, Proxima Centauri, the closest star, and it all seems good. Now, Proxima Cen, again, is a pretty slow mass star. So I guess, I'm a high energy physicist. I started in high energy physics, and I find that stellar astronomers are extremely loose with the fact they flatly assert that it's a 3,000 degree star, and then you go look at a Hertzsprung-Russell diagram, and that's really more like, this chart says 2,800 degrees Kelvin. Proxima Cen is about 3,000 degrees Kelvin. And so it's really close. It's really tempting to imagine that we might have neighbors on Proxima Cent that we could commune with and drink beer with. But now I do note that the temperature, it's interesting, that 3,000 degrees is sort of an interesting temperature to an optically inclined person, because that's actually the temperature of the filament in a quartz halogen lamp. And so these are, here we are, we have quartz halogen lamps, and it's a pleasingly warm red color. Whereas you go in the sunlight, there's all this blue light. So, you know, as you sit in your beach house on Proxima Cent, it's a sort of a sunsetted Earth with a blue sky. It's gonna be even warmer on Proxima Cent. So, if there are people on Proxima Cent, this is what they're, and it's also much closer to Proxima Cent, so it's going to be bigger. Photoshop. The really funny thing is that Yuri Milner has actually funded an initiative called Breakthrough Starshot. Yuri Milner made billions of dollars doing something, and has this Breakthrough Foundation. He's funded a number of search for extraterrestrial intelligence programs. And when he heard about Proxima Cent, he's actually paying people a lot of money to think about making these solar sails. Well, they're not solar sails. They would be powered by an array of extremely, each one of these lasers is extremely high powered. And so all of them together are even more. And then there would be these very, very gossamer light sails that you would push with the lasers. In the middle, there would be a little tiny integrated circuit that would have an antenna and could send pictures back to Earth. Very ambitious stuff. You know, what happens when you hit a piece of, foil that you wrap your food in with a terawatt? I don't know. It's tricky, and the challenges of having enough power to power that chip and send the message back. But he's investing in this, and it's happening as we speak. And people are making chips and trying to build new lasers, and maybe someday we will actually be able to send a chip-sized spacecraft to Proxima Cent. So, as I said, I'm a little early. There was a little of my material got lost in the wash, but I think I'll stop there and take questions.
Questions, please? So can I start? So is our solar system weird? Because I also think it was so beautiful. It was very regular. All the dense things near to the main star, all the non-dense things. Do you think it will be typical, or it will be a strange case?
Well, I actually had one of my movies. Sorry.
Sorry about
no,
that.
There's no typical. I mean, it just, any dynamical configuration that you can imagine has probably already been found. Well, probably not. But it covers a lot of phase space, and every time you think, I mean, 4 stars. I mean, how could you have something orbiting 4 stars? It just doesn't seem dynamically possible, but it is.
I understand that you have been researching also the atmospheres of planets. Is there any result already on this? Exoplanets.
If you come to the 3rd,
okay.
lecture 1.
Oh,
that's all, and no movies.
Okay, so you're going to talk about that. Okay.
Yeah, that's my plan for that.
Thank you.
Hi. How typical would be a North cloud around other extrasolar systems?
I can only comment that there was a paper just a couple months ago where they're seeing, they actually are seeing, it turns out that when you look at the transits, they're seeing that a whole bunch of the transit events are sort of they're not little square. They're not square occultations. They're tapered, and so they really think that they're seeing something with a cometary shape. It's they're seeing something that's not a hard disk. It's a long sort of cometary structure. That's pretty new. There's always the chance it's not going to hold up, but there is at least one example now. Probably. It was in Nature, so. Right, we don't. Yeah, we haven't seen the Oort cloud.
You mentioned most of the famous beasts. You haven't mentioned Tabby Star, which is yet another object which ended up on the news.
What's that?
Tabby Star. I can't remember.
Oh, Tabby Star. Yeah, that's one that has life on it, or yeah. No, they're.
All the comets and.
Yeah, right. Oh no, but well, they're. You kind of have to pick and choose. People have their favorites. If you ask 10 people working in the field what their favorite, most interesting exoplanet is, you get 20 different answers. Yeah, no, Tabby Star's really fantastic too. I don't think it's science. Well, there are things like Avi, my colleague Avi Loeb, who loves to say outrageous things. Says that the way you would look, for instance, look for evidence of intelligent life would be to look for organic molecular disequilibrium, organic content consistent with fossil fuel burning, because the probability is that intelligent life will be as stupid as we are, and they polluted their atmospheres. And you can apply these interpretations as the data rolls in.
More questions? If not, let's thank you, Andrew. Now we break for lunch. I advise all of you to wear your name tag so you can enter the buildings. And let's reconvene at 2:15. Okay? Thank you. Don't try the main students' restaurants. It will be full of calories.